Right. Good afternoon, good morning, or good evening, depending on where you're joining from. I'm your host. My name is Michael Petch, and I'm the editor-in-chief of 3dprintingindustry.com. Few little sort of housekeeping issues before we sort of get into the main event. Please feel free to introduce yourself in the chat if you're joining us. This is a live event. It is interactive. You'll be able to ask our guests who are joining in a moment questions directly as well. So please make the most of that. If you'd like also to ask any questions, there will be a sort of a prolonged Q&A session after we hear a bit from both speakers. Please do add those questions to the Q&A area. That just allows our team to maybe access those, make sure that any questions we don't get through today can then be sort of followed up afterwards. So I'll just put a little sort of example question in the Q&A sort of button there, so you should get a little notification. Right, so today we're going to be talking about next generation functional soft seals for aerospace and defense, and enabling those applications is a material which has much broader sort of reach than just those particular applications. So that's silicone, and printing silicone is challenging, but the company who are joining us today, 3DS Dynamics, have certainly found ways to overcome those challenges and become in a relatively short period of time, sort of market experts in their domain. So I'd like to bring two people who are both co-founders of the company on stage. Please welcome, if you could, Julien, who's the CEO and co-founder, and Edwin Cortel, who is CSO and also a co-founder. Gentlemen, welcome.
Welcome, Michael, and thanks for the
opportunity to
talk today.
We've been talking a little bit backstage, and you were telling me that this is going to be the world premiere of something quite exciting. So you wouldn't even show me the video yet. So I'm keen to sort of keen to see this as well. So I'm going to be hanging around to keep an eye on this. But let me turn the event over to you, and I'll be back in a little bit. So please take it away, gentlemen.
Okay, thanks a lot, Michael. And then now I will share the screen and we start the presentation. So yeah, now let's start. So yeah, we are happy to present today like the next generation of functional silicone soft seal for aerospace and defense, and that will explain to you how we produce it, how we develop them. And so let's start about this. So just first start with small presentation of our company, 3D Dynamics, and also the process, the additive manufacturing process that we develop, which is a dynamic molding. So first, who we are. So we are a French company created back in 2020 with three scientists, so Christophe Marquet, Edwin Courcial, and myself, and based on a new additive manufacturing process, so named dynamic molding, which we apply now for silicone material and also what we call enhanced silicone, so composite material. We will explain to you a bit later how it works. And so we are based here in Lyon, so east of France. Just going directly to the topic. So what are the main limitations nowadays with the industry, with silicone 3D printing and also the traditional processes such as molding, injection, is that it is pretty hard to have custom-made design. So you have a main limitation in terms of geometric complexity. So you cannot access to any kind of optimized design through a mold. So that's where 3D printing gets a lot of sense. And also, if we talk about the development, the time and costly development, because each time you use a mold or a specific formulation of material to enable a specific geometry, it can take more than 3 months to get the mold. And the cost, especially for silicone material, the cost of the mold can range from like 50K to 200k euros. So pretty expensive, especially if you want to have a lot of iteration. And now also another like drawbacks of this is also the limitation in terms of multi-material, like how you can have multiple function on the same material. And to do that, now the only way is to functionalize the material with additive that are often unstable in the material, and that can be also some kind of pollution over time. And the last point is the lack of industrial flexibility. Each time you develop new material, new design, it takes like time to qualification, and also the time, basically the time to market to bring this innovation on the market. So based on all these aspects, the idea we get was to develop a process that combined the best of traditional techniques such as injection molding and the best of 3D printing. So if we come back to injection molding, of course, you can have a lot of already qualified material, injectable material, silicone. You can find more like 10,000 different grades of material. You have fast also productivity, and of course the best of 3D printing, which is the customization, freedom of design, fast design iteration. And what we bring more with this hybrid technology, which we call dynamic molding, will be the fact that we can also get new composites with this brand new process. And so how it works. The main idea was, if you know 3D printing, was to get rid of gravity. Because when you print a material layer by layer, at the end of the day, it will just collapse under its own weight. So the simple idea that Edwin and Christophe get was to print inside a big sand bath, so in a powder environment. Basically, as you can see on the scheme, we immerse the printed inside this huge granular environment, and then we start to inject the material, print the object. And then the powder will just deform and constrain the injected material, as you can see here. And then you will build layer by layer the material. And meaning that as you get rid totally of gravity, you can print whatever viscosity of material, so compatible with all injectable material. You can print whatever design you want and whatever size. And at the end, you can get two different kind of objects. As the powder can mix with the silicone, you can either keep the powder inside to get a composite object, or you can decide to remove the powder that mix to get pure silicone material. In that webinar, we will focus more on how we get composite objects, because the process is compatible with a large range of industrial powders, so you can tune the properties of the composite the way you want. So just a small video to show how it works. So you will see like the scheme. So basically you print inside, the powder deform, self-repair. You never print in the air, so always constrained in this powder environment. And at the end, basically, you can have also the video showing in live how it goes. You print inside the powder, and then you remove the object that has been printed. And the beauty of this is you don't waste any material. Basically, the powder that you remove after the printing, you can reuse for the next printing. So it is purely additive manufacturing. So in terms of competitive advantages, rapid production in small batch, 70% of reduction in lead time. And what is great for aeronautic and defense, the minimum of quantity is 1 compared to like molding when it is like 500, 1,000 or even 10,000, the minimum of quantity. And of course, you can customize the way you want the object. And what we are now the only one to do is that you can really functionalize the material. So you can bring whatever property you want just by playing on the silicone from one part and the powder in which you print on the other part. So just few highlights about the freedom of design that you get. You can see few video. So this is the textile-like structures. You can see you can print all this in once. Then totally self-supported material, you will see. And what is great is you maintain in terms of mechanical properties for pure silicone between 80 and 90% of the property of the raw material, so the injectable silicone. And you can see a full range of different geometry that we can achieve with this. Other thing which is quite important is, as I was saying, we can work with any industrial silicone. As long as it is injectable, you can use in the process. And basically, you can tune from 1 to 90 Shor A. So you can really play on any kind of silicone, which is what we are the only one also to do right now. So you have your industrial silicone grade, you give us, we can use it in an additive manufacturing process. Then another way of playing with the properties, you can change the mechanical property almost the way you want. As you can see on this small video, on the left, you have a 50 Shor A silicone, classical one. Then you can even change the silicone during the process. Bottom part, 50 Shor A, top part, 10 Shor A. Or also, another way, you can change the powder in which you print. You will see on the right, the last below. Basically, you start with a powder that you will keep in the silicone. You create a composite with almost no elongation. And on top, you have a 50 Shor A silicone in which you have removed the powder. So you have 3 different ways to play on the mechanical properties. And of course, what is of great interest to you, and Edwin will talk a lot about this later on, is that as you are compatible with most of the industrial powder, we can tune the properties. We can print in conductive powder, electromagnetic one. We can print in mineral powder to create fire resistance material, or you can just reinforce the silicone with like other kind of particle in which you print. So in terms of production tools, so you can see on the left, this is Christophe Marquet, so one of the inventors that is not here today. We start with this kind of machine that we did ourselves, basically, in 2020. In 2025, this is how the machine looks like. I will show you a video, but it is not only a 3D printer, it is an industrial machine to produce in series. As you can see on the left, it doesn't even have to work with cartridge. It can work even with like pail of material to have a continuous feeding of silicone inside the machine. So this is how the machine looks like. With this machine, you can even print like almost 1 meter cube pieces, either with one print head, as you can see here, or if you want to double the productivity, you can also print with double printed at the same time. I can show you. This is how it works in the powder. And then I will just move a bit up. There you can work with pail of material that directly feeds into the machine. And then now you can work with multiple printed at the same time if you need it to increase productivity. This is really meant for series production. And you can see basically the printed dancing in the powder bath. And then at the end, just as simple as that, you will remove the pieces that has been produced directly inside the powder. And for those who knows a bit, it is a paste seal for aeronautic, these pieces. And then, as Michael was mentioning, we are pretty happy to show you first premiere the video of how we will make our production line evolve. Because now we will go not from Cartesian 3D printer, we will go for robotic 3D printer to make the production higher, more productivity, bigger pieces for aeronautic up to meter. And then you will see how the robot will work together. So up to 4 robots working at the same time. That you will see like powder material that you inject to create the mold. Then 4 robotic arms working at the same time on the same pieces, starting from different points. And then it will basically make the production like faster, more reliable, design in terms of design, more complex design, and fully the fully automation as well. Then after the printing, you have the curing process to processing the silicone. And then after that, just the cleaning, like in any process. You get back the object that has been cross-linked inside the powder environment. And then after that, you will see the full production line, dimensional inspection, surface treatment, if you need like a post-treatment, of course. And then dimensional and functional conformity, and then packaging. So basically, this is the line we are developing right now and fully powered by artificial intelligence. And Edwin will explain to you a bit more what is the aim of this line. But you can see that this is how you make additive manufacturing to the 21st century. So fully automation. Then before I lead the word to Edwin, few highlights about the market we are targeting, of course. So aerospace and defense. So basically, we tackle the main cost driver in aerospace and defense, having all the properties all at once: lightweight, durable, optimized design, of course, and new functionalities. And to do that, of course, we have a special offer when we work with industrial, OEM, Tier 1, feasibility study, rapid prototyping, but most of the time it is a build to spec or a build to print approach, and then going pretty fast to small and medium series. And of course, with the minimum of quantity, that is one, which is pretty interesting for series production, but also to test a new concept. With these three applications that we target: airframe seals, or just protection against air, fluid, and gas leaks; thermal protection, so resistance to extreme temperature. So for those we know the ISO 2685, basically how you can have a material that withstand more than 1,200 degrees for 15 minutes in kerosene fire. So it is gasket for engine, basically. And of course, with all the arrays of defense application, having the ability to develop electromagnetic interference seals, so protection against electromagnetic interference, how you protect all the electronic device within any aircraft or even other vehicles. And you can see that the aerospace silicone market mainly drive by the production of seals, gasket, will reach even more than $1.5 billion by 2026. So it is a pretty nice market to address right now, and pretty rising market. And as I was saying, to address this, we produce so either on build to print, so based on your technical drawings, or on build to spec, what we prefer, because we can develop and design the pieces according to your exact specification. And basically, this is how we managed to have the first pieces qualified for fly in 3 months instead of 2 years. And now that can fly with an helicopter in a military program. So electromagnetic shielding and gasket, basically, you can find in any application for aircraft, either civil or military. So helicopter, aircraft, drone, whatever things flying, you can find a gasket with fire seals and electromagnetic shielding application. Because electromagnetic and fire protection are really the key requirement for safety and performance, because from one side, you need to protect all sensitive electronic systems from external electromagnetic interference. Basically, how you make your aircraft safe and also invisible. On the other part, you need to have compliance with the fire resistance. Why? Because you can be exposed to high temperature, especially in engine, to prevent any flame propagation, and of course the smoke and toxicity emission. So you need to have really high added value seals to make all of this work. Because it can, even when you talk about electromagnetic interference, it can come from basically anywhere, from lightning, from satellite, radar, or air traffic, even from household device. So you need really to protect all the critical electronic device within an aircraft. And this is like few examples to show you that we can find find fire-resistant seals or even EMI seals in any part of helicopter, as you can see on this drawing, or in any kind of aircraft, any part, you can find this kind of seals. So even without knowing, you know it is basically anywhere. And you can, especially like for engine, this is why you find application basically for fire seals, because you meet like extreme temperature, so you need to have like really high added value seals in that case. And so on this, yeah, just to finish it, basically we work with main actor in aerospace and defense right now, like Airbus, MBDA, Amphenol, Dassault, Duquesne, and FIR. So it is really turning into a new product. And to finish, what you have to be, before I give the word to Edwin, what you need to think about our process is really one of the first process to shape and functionalize silicone at industrial speed and scale, with full design and material freedom, tool-free manufacturing, because you don't need any mold. It is versatile and scalable, and of course, it is eco-friendly because you don't waste any kind of material. And on this, I will leave the word to Edwin Courcial, my co-founder, that will go more into the detail of the application that I present to you.
Thanks, Julien. Hello, all. Happy to be with you today to explain more about our products for aeronautic and defense markets. So in this part, I will focus on one key application of dynamic molding, the electromagnetic shielding. We will see how this technology allows us to create soft, high-performance composites that can ensure protection across a wide range of frequencies. So, as Julien explained before, modern aircraft constantly operate within an invisible electromagnetic storm. Some fields come from outside, radars, satellite links, communication networks, event lighting, while others are generated inside by power systems, sensors, and avionics. Together, they cover a broad spectrum from kilohertz to gigahertz, interacting dynamically as the system gets denser and more digital. The result is not a single wave, but a complex superposition of multiple fields evolving with each flight phase. Our challenge is to maintain this electromagnetic compatibility by protecting the aircraft most sensitive zones, antennas, radars, electromagnetic bays, and structural joints, without adding weight or sacrificing the flexibility of materials, of course. This is why we develop soft, adaptive shielding materials capable of conforming to any geometry and providing reliable protection where it truly matters. And what's exactly what we will look at next, where these seals can actually be located across the aircraft. So in aeronautic and defense, electromagnetic sealing is not a niche application. It's everywhere. And electrical and electronic system interface with the aircraft structure. Here we can see a few representative examples on fixed wings aircraft. EM seals are typically used around radomes, engine cores, access panels, and connector interface, wherever signals enter and exit the fuselage, or where the structure must remain both sealed and conductive. The same logic applies to rotary wings platforms and unmanned systems like drones, which integrate more sensors, antennas, and communication modules than ever before. In all these cases, the challenge is the same: to ensure continuous shielding performance despite mechanical stress, vibration, and environmental exposure. And that brings us to the next question. What are the technical needs that a material must meet to perform reliably in these conditions? If we now look at the problem from the product's perspective, our goal is to design an electromagnetic shielding gasket that combines mechanically flexibility with high attenuation performance. Such a component must ensure environmental sealing, protecting against fluid condensation and contamination to guarantee long-term system reliability. It must also remain mechanically compliant, of course, keeping uniform contact pressure without damaging the interface. At the same time, it needs effective multi-frequency shielding from kilohertz to gigahertz to handle both internal emissions and external electromagnetic exposure. Most importantly, the shielding level, typically above 80 dB, especially for defense market, must stay stable under real operating conditions, even during compression, relaxation, or cyclic strain. To reach this specification, we rely on dynamic molding, a process that combines silicone with conductive powders as dynamic mold, acting as dynamic mold. This approach couples formulation and shaping in the single step, producing enhanced silicone, soft, conductive, and durable materials. So in this webinar, I will stay focused on two scientific challenges that define this technology. First, how to maintain shielding efficiency under mechanical load, and second, how to guarantee continuous protection across the entire frequency spectrum. So the dynamic molding enables the design of enhanced silicone with a well-controlled biphasic structure. A silicone matrix around 35 volume%, providing elasticity and compliance, and a micrometric powder about 65 volume%, responsible for electromagnetic shielding. The specificity of this material lies not only in this ratio, but in the spherical morphology of the conductive particles. These spheres ensure excellent flowability of the powder when it acts as dynamic mold, while simultaneously creating interstitial voids or dead volumes that allows the silicone to drain in and fill the structure during the processing, during the dynamic molding, I mean. This, this mechanism is essential. It gives rise to an isotropic microstructure where the silicone phase constitutionally coats the conductive particles while maintaining their connectivity. The results is a three-dimensional percolated network that ensure uniform conductivity and shielding efficiency, reaching more than 112 dB at 1 gigahertz. This microstructural design illustrates how the geometry of the filler directly controls both the manufacturing process and the electromagnetic performance. The next step will be to evaluate whether this performance remains stable across the full frequency range and under mechanical load over time. The electromagnetic shielding performance of our enhanced silicone was evaluated using coaxial transmission line setup, following the ISTM D4935 standards. As we can see, the red curve shows an attenuation level above 80 dB across the entire frequency range from 100 kHz to 1 GHz. This confirms that our formulation provides a high and stable shielding efficiency over multiple frequency decades. It's unique. For comparison, the black and green curves correspond to other material that we have in 3Deus, cross-section or alternative formulation showing lower performance and narrower effective bands. The overall shape of the curve indicates that our materials operate mainly through reflection-dominated shielding rather than absorption. This behavior is consistent with the conductive percolation network within the silicon matrix, ensuring efficient reflection of incidence electromagnetic waves across the test spectrum. Now that we have validated the shielding performance under static conditions, the next question is, how stable is this connective network when the material is deformed in tension or compression, as it will be in real joint under compression again and tension? To evaluate how stable the electromagnetic shielding remains under mechanical load, we develop a couple tensile electrical measurements. The setup combines a standard tensile test with in situ conductivity monitoring through brace electrodes, a customized version of the STM D412 mechanical protocol. Here, we don't measure the shielding directly, but the electrical conductivity, which correlates to the electromagnetic performance throughout deformation. In short, stable conductivity under strain means a stable conductivity network and therefore consistent shielding capability during use. The plot on the right shows both the mechanical and electrical behavior of switch silicone filler composites. The red curve associated with the conductive powder 1 demonstrates the best balance between elongation at break and preservation of the conductivity. This indicates that the percolation network remains connected even under large deformation, while the other formulation lost continually earlier. Overall, this experience confirms that our selected silicone filler pair maintains its conductive network under strain, meaning our materials can retain its shielding efficiency under real operating conditions as required for flexible seals in aeronautic and defense application. So now in this slide, the goal is to present the full identity, the full idea of our end silicone designed for electromagnetic shielding application. It's a flexible composite, of course, exclusively produced through dynamic molding, a process that uniquely couples formulation and shaping. Its shielding performance exceeded 80 dB, meeting military standard across a wide range from kilohertz to gigahertz again. The material exhibits an electrical conductivity close to 82 Siemens per centimeter, and its mechanical property range from 50 to 80 Short-H, with elongation at break approaching 100%. Beyond shielding, it offers strong resistance to fluid, particularly through encountered in aeronautic and defense environments, and demonstrating long-term durability with a lifetime exceeding 7 years under wide atmospheric conditions. Production is achieved with dimensional tolerance around 100 microns, and the material is also resistant to salt and dust exposure. Importantly, our formulation is P-phase free, aligning with the latest environment and regulatory requirements in aerospace. And finally, the cherry on the top, the environmental impact of producing 1 meter of this gasket is extremely low, really equivalent to a single washing machine cycle. In other words, we have achieved the paradox of manufacturing a soft, high deformation P-phase gasket with metal-like shielding performance, all while keeping its environmental footprint minimal. So now let's go to the thermal and fire resistance part. So after exploring electromagnetic shielding, we now move to another critical function for aircraft safety, the fire protection. Using the same dynamic molding process, we design enhanced silicone tailored for thermal and fire-resistant sealing, capable of protecting aircraft structure under extreme conditions. Fire is one of the most critical threats for any aircraft, whether it's an airplane or helicopter. If not immediately contained, a local fire can rapidly propagate through the structure, compromising key system and ultimately leading to catastrophic failure and loss of life. In this context, understanding where and how fire can occur inside an aircraft becomes essential. Engines, fuel lines, electrical base, and structural interface are all potential ignition or propagation zones. That's precisely where high temperature and fire-resistant seal act as the vital organs that isolate, protect, and delay flame propagation. From its physical standpoint, heat transfer in such condition can occur in three ways: conduction, convection, and radiation. In this webinar, we will focus on convective mode, representative of forced airflow condition encountered during engine and external fire scenarios. Our work specifically investigate fire stop silicone joint exposed to this environment through dedicated fire resistance test. So when designing fire resistant joint for aeronautical or defense applications, several requirements must be met simultaneously. First, the joint must ensure sealing performance, protecting against fluid such as oil, kerosene, or hydraulic liquids commonly found in aircraft environments. Second, it must retain mechanical flexibility, allowing for deformation and compression without losing its sealing or structural integrity. Beyond that, the joint must demonstrate fire and thermal resistance, withstanding extreme temperature and direct flame exposure for extended duration, as required for the most demanding standards such as ISO 2685. Finally, all of this must be achieved while maintaining lightweight performance, an essential constraint for aerospace design. To meet these multiple constraints, we rely again on dynamic molding process, of course, which enable to the direct formulation and shaping of enhanced silicone. Here, the silicone brings chemical inertness and elasticity, while mineral powders are incorporated within the matrix to enhance fire resistance. This combination allows us to produce lightweight, flexible, and durable fire protection joint capable of resisting the most severe operational conditions. So here you can see a video. If you can launch the video, please. Yes, thanks, Julien. This video illustrates the fire-resistant test performed according to the ISO 2685 standard. In this protocol, we evaluate a fire stop joint produced by dynamic molding made of silicone combined with a mineral powder, which is QTZ grade in 3 layers. The sample is exposed to a kerosene flame at a fixed temperature and heat flux density, representative of the condition faced by aircraft structures during engine or external fire. The goal of the test is twofold. First, to ensure that no flame or hot gases penetrate through the backside of the assembly, and second, that no residual flame remains once the exposure period ends. To reproduce real in-flight conditions, the joint is placed between two metallic plates subjected to controlled vibration, simulating the dynamic stresses experienced during operation. At the end of this test, as you can see in this video, our joint successfully maintained their integrity, no flame breakthrough, no residual ignition, and stable performance throughout exposure. These results confirm that our enhanced silicone produced by dynamic molding fully meet the ISO standard for aeronautic and sealing application. So now to the next slide. What we see here is the microscopic evidence of the mechanism that make this fire seal effective. One on the right, you can observe the initial microstructure of the joint directly obtained from the dynamic molding process. It consists of silicone matrix intertwined with mineral powder domains, some of which remain intentionally entrapped inside the structure during fabrication. These internal pockets are key to the material's thermal behavior. They form diphasic regions made of air and solid mineral particles, which provide both deformability and thermal resistance. Now, on the left side, you can see the same material after exposure to the ISO fire test. At this stage, the surface morphology has completely changed. The mineral powder has undergone a partial sintering and vitrification process. The spherical particles have fused locally, creating a continuous glass-like crust that seals the outer surface of the joint. This vitrified layer acts as a self-formed thermal shield, drastically reducing heat transfer and preventing oxygen diffusion towards the inner silicon phase. This transition from a flexible composite to a semi-ceramic protective skin is what makes the architecture unique. During normal operation, the joint remains soft and compliant under flame exposure. It's self-organized into a rigid insulated barrier. Such a reversible behavior, flexibility in service and protection under fire, is directly enabled by the control of microstructure during dynamic molding. In short, the micrograph illustrates how materials design and process architecture converge to transform a simple silicone into an adaptive, self-protecting system. So with dynamic molding there, you can see that we can create, according to the customer needs, different shaping of external and inner shape that can be very thin or bigger. So this flexibility makes dynamic molding a universal method for producing lightweight, high-performance seals with architectures tailored to their function. So to meet, on the next slide, please, Julien, to meet the specific industrial requirements, we relied on a fully integrated design to manufacture workflow. It starts with the digital model of the joint, from which we define both the external geometry and the internal cavities. Then, using our database of materials, we simulate the mechanical and thermal behavior of the joint under realistic operating conditions. Our models account for hyperelastic deformation, the Mullins effect, and heat transfer by convection, allowing us to predict the performance of the final component before fabrication. Once the design is validated through simulation, the part can be directly produced by dynamic molding, reducing iteration time and development cost. This combined approach, simulation-driven design and additive manufacturing, enable us to move from concept to functional prototype in just a few days, as Julien explained before. Some things that impossible with conventional molding technologies. So And this is also the idea of this kind of enhanced silicone. So there we can produce the silicone with hardness between 65 to 75 short A, with high elongation at break, with the same also resistance of fluid and durability that we present before for EMI gasket, and also a very low environmental impact, and of course PFAS free. So on the last slide, to conclude, let's summarize with dynamic molding truly brings. So first, dynamic molding is the only additive manufacturing process that formulates and shapes in a single step, creating hand silicone with tailored functionalities. It enables the production of both electromagnetic shielding joints and fire protection seals using the same technological foundation. Second, the microscale synergy between the powder and silicone gives rise to unique material architecture. This controlled microstructure allows us to integrate conductivity, thermal resistance, or mechanical compliance without compromising elasticity. Third, dynamic molding stands out for its low environmental footprint. It operates at room temperature without solvent, with recycled raw materials and minimal energy consumption, combining performance and sustainability. Finally, it's a process built on design logic. Because formulation and shaping happen simultaneously, every product becomes the result of a design strategy. We no longer just manufacture materials, we engineer function. That's the real strength of dynamic molding, turning fabrication into creation. Thanks for your attention, and it will be a pleasure to give you answer for your question.
Superb stuff. Very, very eye-opening, and yeah, remarkable to see those 4 robots working together there across, what was it, 8 steps? I think I counted, without sort of any human sort of interventions. Really sort of dynamic project that opens up so many sort of applications, I think, longer term. I've got a couple of questions that I've been preparing. I'm taking a few notes. Obviously, we've tried to make sure we can get to our questions from the audience as well. And let's jump in talking a bit about some of the practical adoption advice, maybe. How can service bureaus or OEMs start getting into these regulated aerospace markets using your technology?
Yeah, that's a good question. And basically, that was the idea we get when we created the company. It was just we use additive manufacturing for end-use product. So at the end of the day, basically, additive manufacturing is just a mean to produce. What we want to have is the final function. And that's why we say we work also with healthcare application, but now a lot with aeronautics. How can we produce material without any certification? And the quality system, the QMS, is the key, because you create entry barrier, because you work on highly regulated market. And for me, that's the next step for additive manufacturing, is really to bring high added value pieces, because when you use additive manufacturing, either you save life or you improve product. And for this, you need to work in high regulated markets.
How do sort of tooling and lead times compare with conventional approaches to the molding of silicones?
There is 2 ways. So of course, when we have a first study, you have like non-recurring costs. You can have a study that will last maybe 1-2 months when you want to optimize the product. But at the end, when everything is set, the delivery day for us is 21 days. So yeah, this is why we tackle the industry with this short lead time. Yeah.
Edwin, I know you've worked very sort of closely on this robotic line. What's changing here? Is it going to be cycle time, consistency, QA, or maybe tell us a little bit more about this dimension of automation and scaling?
Yeah, it's an interesting question. Thanks. So the goal of the robotic line, as you have saw in this video, the goal is to go faster and move to a full freeform of move to freeform, real freeform additive manufacturing process, which is able with 6-axis robotic arms. Then also use multi-robot to print same pieces, 3D pieces. Is also the goal to go in industrialization and go faster. And then with the AI-powered system to go to the full automation and let's say have an additive manufacturing system and production line that can challenge the injection molding, the cadence of the injection molding that we have with other companies.
Helps if I unmute myself. What are the so in terms of sort of placing this into strategic context, right? What are the main drivers behind this? Is it defense? Is it sort of retrofits, or is it sustainability?
Actually, it's a bit of both, actually, like, because for the next generation of manufacturing process, what we call smart manufacturing, you need to have like eco-friendly process, because at the end we need to protect the earth as everybody does on a daily basis. And also you need to have like new functional material. You need to have like more efficient material. And that's why also with the AI community system that we develop with the robotic line, it is not only about the material, what is important, it's also about the design. And so when you can combine eco-friendly process, optimized design, and short lead time, basically you can tackle defense application that's, of course, now, unfortunately, what we can see on a daily basis. You need to be able to iterate fast. And that's why trigger also, that's the main driver today. More efficient material and faster lead time. And of course, eco-friendly. So bits of both, actually.
And on this sort of business strategy or business model, what is dynamic molding? Is it licensed? Do you partner, or how does this work? Sort of commercial.
What we decided, and that was the key vision with the 3 co-founders, is that we wanted to develop an industrial facility to produce and use product. But of course, at the end, depending on the customer we have, it can be OEM, it can be tier 1, tier 2. Out of collaborative project partnership, the manufacturing process can be licensed, of course. If people want to internalize the process, this is something that can be discussed with us. We produce normally, but at the end, if people want to internalize, we can enter into a discussion to do that. But we don't sell machine right away. This is not our business model. But licensing the manufacturing platform can be something, that we can think about in the short midterm.
Let's take some questions from the audience, because there are a lot of questions in, and I want to make sure we can get through as many of these as possible. So here's one about other materials. Are you considering other materials, 2 parts or single part liquid deposition? And is viscosity taking a big factor to be applicable in this system? And that's from Eunice at Nike.
First, hello, Eunice. Good to talk to you again. Yeah, actually, we talk about how we start to investigate a lot of material. I think Edwin can give a few ideas, but yes, this is something that we take into account.
Yeah. In fact, we can print different kind of materials, especially silicone, because you can find silicone in two components or one components, but it could be also the same for polyurethane or some different thermoplastics. So this is what we also validate in research but the goal there for aeronautics and defense, it's more focused on silicone, and especially for two-component silicone. The question of viscosity is a real question. The key to understand the know-how of dynamic molding is in the rheology world. So, yeah, the fluid rheology and also the granular rheology. So to meet these two worlds, it's not easy, but it's very exciting every day in 3Ds.
And just maybe to have last thing on material as a teaser, yeah, it can work with metal, thermoplastic as well. Just a matter of investment, of course, but the proof of concept is already there. So yeah, as long as you can inject, and as Edwin was saying, going to the right rheology of the material, right viscosity, actually it is compatible.
A couple of practical questions. Maybe we'll roll these into one. So the first question is about when you print and powder remains inside, so you've got a composite part, can you get rid of the powder inside afterwards? And the second question, which is also related to sort of practical natures here, are what happens to the uncured silicon when you're printing? So who would like to see those two?
It's for me, Julien.
Yeah, if you want
Okay.
to go.
So on the first question about the powder that we can remove after printing, so we have different powder, and it's possible to use sacrificial powder. So you select a powder as a dynamic mold to print the silicone, and according to the handle of interface between the silicone and the powder, you can obtain a pure silicone at the end. And even if you have some powders at the surface, it could be possible to remove with non-solvent way, just by water. And on the second question, so on the uncured silicone, so yeah, why it's a dynamic mold? Because the silicone from the beginning to the end of the printing process is fused mode. It means that it's a pure liquid silicone up to the end of the 3D printing process by the dynamic molding. Then after that, the goal is to go to a thermal curing step. This is what you saw, I guess, in the video, to cross-link the silicone and obtain the silicone rubber at the end.
And actually, that's drive our business for the first question. With when we can remove the powder to get pure silicone material, this is where we tackle either the healthcare industry, being able to work with medical grade silicone, but this is also the way we can have also, when we didn't talk so much about it today, but the airtime seal, we can just work on pure silicone seals, just the way of how we remove the powder to get the pure silicone. But yeah, this is what we developed the past 2 years. Yeah.
I think we have time maybe for a couple of quick questions. So let's put this one up. Okay. Oh, there we go. So this question is about how you examine porosity, right? Sort of how do you go about looking at porosity, and what are your sort of findings there?
Yeah, good question. So in a previous PhD thesis, we also demonstrate this the volume that you can obtain with the powder inside the silicone. So it's a real challenge in the dynamic molding. The dynamic molding is not just a process; it's a real concept that you have to handle to understand what is possible. I mean, why? Because of course you have to manage the rheology from the fluid, and also the granular part, which is the powder, but also the interface. And wow, it's you met three kind of science, and yeah, it could be a healed post problem, but yeah, the interface and how the materials can met together during the 3D printing is a real challenge. And if you understand that, you can print as a EMI gasket or fire-resistant seal to solve the paradox of different composite that you need for this kind of applications.
Superb. So unfortunately, we've actually reached the end of our time here today. But we will be making this webinar available for replay. A few people have asked that. People can also contact you directly, right, if they've got questions. I think you put your email up earlier. And of course, I understand you're both going to be, or Frides will be in Frankfurt next month with the rest of the industry.
We will not miss the show.
Superb. So lots of opportunities there to sort of find out more about this very exciting process, which really, opens up applications in the materials that the customers actually want, right?
Yeah, that's what we want to do. Open a new application.
Thank you very much for joining us today, and thank you for everybody who also joined to watch and who had questions. So Edwin and Julien, great to see you both. Thank you.
Yeah, thanks for the organization of this, and feel free to reach out if you have any question. We will be happy to.
Yeah.
Superb. Okay, everyone, have a great rest of the day. Thank you.
Thank you all.
Yes, you too. See ya.